Alright, this is the second part of sets. We're going to talk about how a set can be well defined, and we're going to talk about how we write out sets so that we can tell if something is a member of a set. A set would be well defined if you can determine if any item is a member of the set. For example, something that wouldn't be well defined great songs is not well defined. Why isn't great songs well defined? Because if you take a song like, I don't know, YMCA, to one person that might be a great song, but to another person that might not be a great song. So you can't really tell if that's part of the set or not. So great songs is not well defined. However, English alphabet is, because you can tell if something is part of the English alphabet pretty easily or not. So that would be well defined. When I say something like 4 is an element of the natural numbers, the notation looks like this. 4. It's a capital E, but it's small. 4 is an element of n. So this symbol means is an element of. The meaning is that 4 is in the set n. The truth value. Is that true or not? Is 4 a member of the natural numbers? The truth would be yes. True. Because 4 is a natural number. It's one of the counting numbers. Let's try another one. This one says -3 is not an element of natural numbers. The notation would look like this. -3, and we'd have the element symbol, but we put a slash through it to mean not in n. -3 is not a member of natural numbers, and the truth is yes. -3 is not a member of the natural numbers. That's how this E letter works. E means in, or is a member of the set, and that's how we shorthand that. The empty set. Occasionally, there's going to be a set with nothing in it. If a set doesn't have anything in it, it's called the empty set. Well, the empty set looks like this. It's a set because it has the braces, and this tells us that there's nothing in it. It's not that we forgot to put something in it, it's that there's nothing in it. So that is the empty set. Set builder notation. Sometimes we can build a set that has multiple members, and we can define it not by roster notation, but by saying what's in it. Here's how it works. We start out with the braces to say that it's a set, and we'll put X to denote that there are members in it. We'll put a bar, let me write out what this means. The set And this is what we're going to be saying. The set of all x, and this bar means such that. So this is the set of every member of that x, whatever x happens to be, such that x is an element of n and x is greater than 7. What this would look like: x has to be a natural number that's greater than 7. So this set would actually look like 8, 9, 10, and so on. These are the actual elements of the set. These are the actual elements right here of this set that is read. The set of all numbers such that x is an element of n greater than 7. X is all of the numbers in n that are greater than 7. We built this set. This is a shorthand form of saying both this and this. Shorthand form. Let's look at it again. Set builder notation. I'll do the first two, you can try the second two. For A, the set of integers greater than -3. Well, we need to have a substantial knowledge of those letters that are associated with the different patterns. So integers are I. So x, such that x is an element of I, and x is greater than -3. That's the set, because x is an element of I, and x is greater than -3. The next one, the set, so braces because it's a set, x such that x is an element of, now the whole numbers, w, and x is less than 100. Once you get the hang of this, it's really not that tough, but you have to understand some of the little nuances. You have to have the bar, meaning such that. Then you have to say x is an element of this part, and it's also fitting these conditions. See if you can try the next two. Go ahead and pause it here if you'd like. If not, I'm going to keep rolling through it. The set of integers less than 9. So x is such that x is an element of the integers, and x is less than 9. The set of natural numbers greater than 4. So all x such that x is in the natural numbers and x is greater than 4. You see how this works. Eventually you'll have to go either way. You'll either have to write it as set builder notation, or you might have to say what elements are in that set. Set stuff. A finite set. If you understand the word finite, finite means the number of elements in the set is a whole number, meaning you can count them. It has a finite number. It's a whole number. The cardinal number, for example, 14, is the number of elements in a set. So for example, if I have a set A is 1, 4, 6, 9, A has a cardinality of 4? It has 4 elements. So it has a cardinality of 4 because it has 4 elements. It only has 4 elements, so it has a cardinality of 4. It is a finite set. Not too bad. So when I say the cardinality of set J, the cardinality is going to be 2. The cardinality of set C is 1, 2, 3, 4, 5. 5. The cardinality of S would be from 3 to 31. It ends up being 29 elements. For E, there's 1 element. It's a 0. What about for T? Well, T goes 3, 3, 7, 51. Well, how many elements does it have? It only has 3 elements. 3 is in there 2 times. So it's only distinct elements. So this has 3 in there twice. Well, the cardinality is only 3 because there's only 3 different numbers. There are no elements. So the cardinality of the empty set is 0. There are no elements in the empty set. It's empty. A set equals a set. What does this mean? A set equals a set if they have the exact same elements. This is what it looks like. A equals B if and only if A and B have the exact same elements. They have to have the exact same elements. So, for example, if I say that DEF is equal to FED, they have the exact same elements, so those sets are equal. Sets are equivalent, so A is equivalent to B if they have the same number of elements. So if they have the same number of elements, so for example, if 2 things have the same number of elements, they each have 4 elements, their cardinality is the same, then they're equivalent. Not equal, but equivalent. Alright, so that's just general set things. So we're going to state whether these are equal or equivalent. Well, if I have A, E, I, O, U, 3, 7, 11, 5, 15, 19. So I have 5 in this, 5 in this. So these would be equivalent. 4, 2, 7, 3, 4, 7, 9. That would be neither. Neither. What about if x is an element of the whole numbers and x is less than 5? And I had my second set was alpha, beta, gamma, delta. Okay. Well, these would be 5, 4, 3, 2, and 1. That would be the elements of the whole numbers that are less than 5 or equal to 5. And this would have 1, 2, 3, 4, 5, 6 elements. So this is neither. They don't have the same number of elements and they don't have the same elements. What about D? If it's 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, etc., etc., etc. And this is all of the numbers that are less than 17, so this would be 1 through 16 in this set. And there are 16 elements in this set because 5 goes into 80 16 times. So they each have 16 elements, so these would be equivalent. Sets are pretty basic. And this first section is really just outlining the pieces of sets that we need to talk about sets. And so I hope that this wasn't too wasn't too difficult for you to understand. We've got cardinality, we've got equivalent sets, we've got equal sets, and we've got set builder notation. Those are very important concepts that you need to talk about in your summary so that I know that you got it. We're going to talk about this more in class. We're going to do a little bit with set builder notation, and that's going to take us into our next discussion of sets. All right, so I hope you learned something today. Thanks for watching. We'll see you next time.